everyone, today we're going to start chapter 14.2, and this one delves a little bit deeper into what exactly are reaction rates and how do we determine them. So the speed of an event is usually defined as a change that occurs in a given time interval. So we're going to be looking at, specifically for reaction rates, the change in concentration of our reactants or products per some unit of time. Our units, and I would write this down in your notes, are typically given molarity per second, because if we remember, concentration, the unit for that was molarity, which is given as a capital M. Please make sure that it is written as a capital M, because if you give me a lowercase m per second, that is meters per second, and I will mark you guys off. Now, there is the law of conservation of mass, so mass has to be conserved in reactions, and because of that law, the rate of disappearance and the rate of appearance is going to have basically a stoichiometric equivalence to it. They're not equal to one another, but if we look at their coefficients, there will be a relationship among them. So here, if I had the equation A yields B, in order to follow that law, note that we started off with 1 mole of gas A and 0 moles of gas B. The total moles in this system is 1. So note that when I look at gas A converting into gas B, these numbers always add up to 1. Same thing here. These numbers always add up to 1. Note as I'm using up my gas A and it's decreasing, my gas B tends to be increasing. So this is what this chart is showing us, is that here over time, as my products, which was A, labeled here, is decreasing, being used up and disappearing, my B is appearing here. So if we were going to give a equation for the average rate of appearance of a product, I would write down this first part, or you can write down this part as well. The rate of appearance is the change in concentration of B. So one thing to know is that the delta sign means change, and the way we find that is by taking our final concentration minus our initial concentration. Notice that we use brackets to illustrate concentration here. Then we're going to divide it by the change in time. So again, we're going to use that delta sign and then a lowercase t to represent time here. Opposite if we're looking for the rate of disappearance. So if we're looking for the disappearance, because this is going to be typically a reactant, so remember usually reactants are disappearing, we're going to be using the same equation, the change in concentration divided by the change in time. The only difference here, notice that there is a minus sign here. And that's using to indicate that I am seeing a disappearance. But don't get confused. Rates are always expressed as positive quantities. I'm going to go ahead and star that. The reason we use a negative there is because our A is decreasing, our change in concentration is going to be a negative number. And so in order to cancel out that negative number and make it a positive rate, that's why it gets that negative sign out front. So here we're going to do an example where it says for the reaction A yields B, calculate the average rate in which A disappears over time. So this keyword disappears is important. The time interval is 20 point seconds to 40 point seconds. If the original concentration was 0.54 molarity and the final concentration was 0.3 molarity. So here we need to set it up as the change in concentration. So remember, it is final minus initial. So 0.3 molars minus 0.54 molarity divided by the change in time. So remember, change in time is final minus initial. So 40 point minus 20 point. And both of these are seconds. And I said disappearing is going to come into play. We have to make sure we put this negative out here. So when you go ahead and subtract the top, you subtract the bottom, and you take into account this negative, you're going to get a reaction rate of 0.012, and it's a positive. And our unit is going to be capital M, molarity per second. Here, my answer has 2 sig figs, which makes sense because 2 here, 2 here, 2, and 2. Perfect. If we're going to do this one, I would like you guys to pause this one and you guys can attempt it to yourself and then unpause it and see if you get the right answer. So hopefully you guys attempted this to yourself. This one's saying for a reaction A yields B, calculate the average rate of appearance. So this one, take into account its appearance over the time interval of 0 seconds to 40 seconds if the original concentration was 0 and the final concentration was 0.460. And it tells us to disregard a time and concentration at 0 for your significant figures because there's no other number you can have. So here, when we set it up, appearance tells me it's going to be positive, and then I need to subtract my concentrations. So 0.460 molarity minus 0 divided by, subtract my times, final minus initial, 40 minus 0 seconds. And when you guys subtract those and divide those out, you should have gotten a positive 0.0115 molarity per second. Here, we're going to have 3 sig figs because I have 3 here, and I also have 3 sig figs here as well. So that answer is good. Now, one thing to note, and I would write this down as well, it is typical for reaction rates to decrease as the time proceeds. So it's very important to write down what time frame are we looking at. Are we looking at 50 to 100 seconds? Because that gives us a rate of 1.7 times 10 to the negative 4th. Or are we looking between 500 and 800 seconds? Again, that gives us a different reaction rate going on here. So again, the reason reaction rates tend to decrease over time is because you have less of a reactant or less of a concentration, so there's not as many collisions for this reaction to happen. So here is our sample problem actually using a real-life chemical instead of just imaginary A and B. So it says, using the table on the previous slide, calculate the average rate of disappearance of C4H9Cl over the time interval from 50 to 150 seconds. So remember, this one's saying disappearance. So again, that's going to come into play. If you want to pause this and try this on your own, you are more than welcome because we're going to go through the answer once you unpause. Okay. Hopefully you had a chance to go through the answer. So let's go ahead and set this up. Disappearance tells us I'm going to have a negative. And then if I subtract my final minus initial on my time interval, I get 150 minus 50. Then you have to go back to your chart and look for those values. So here I have 150, and you're going to see you're going to need to use this value for that. And then here's your 50, so you're going to use that value for that. So I'm going to take those two values and plug it into my chart. So here I get 0.0741 minus 0.0905. And when you look at this and you subtract the top, subtract the bottom, take into account this negative, you're going to get a positive 1.64 times 10 to the negative 4th. Don't forget your units is molarity per second. And I'm going to have 3 sig figs because there are 3 here. There are 4 here, 3 here, and 3 here. So my lowest is 3. So there's my 3. Okay. Now, to finish up this, a couple things that we have to mention is instantaneous rate. Graphs can actually show the concentration of a reactant and product changes with time. And when we make a graph, we can actually figure out and evaluate instantaneous rate. Remember, instantaneous is what is happening at that particular instant in the reaction. And it's determined from the slope of a curve at looking at a particular point in time. So what is the rate happening exactly at 51 seconds? So for example, here they just kind of graphed the information that was given and they can figure out instantaneous rate. Now, to finish up, we've been working with things that typically have a 1-to-1 ratio. So A yields B gives me 1A and 1B. The reaction that we did on a couple slides ago, here my coefficients were 1, 1, 1, and 1. But that showed us the rate of disappearance is the same as the rate of appearance, but that's not always true. And the reason for this is you have to take into account reactions that have bigger coefficients other than 1. So here in general, if I had the reaction A, B yields C and D, A, B, C, and D lowercase would equal my coefficients, and then capital letters would equal my compound. We have to realize that the rates have to be equivalent to my coefficients. So when the way I usually give this is these are all equal to each other. So here I have for A, 1 divided by the coefficient, so whatever coefficient's here. So if there's a 2 here, 2 would go down here, times my rate. And I'm going to put a negative sign out front because this is a reactant, so it's going to be disappearing. This is equal to, if I'm looking at B, same thing, 1 over B's coefficient. And I'm going to put a negative here because it's going to be disappearing. This is still equal to 1 over C. This one does not have a negative because this is a product, so it's going to be forming. And then same thing, 1 over D, and that equal times it by the rate. And it's going to be positive because this is going to be forming. So just note the negative sign shows the rate of disappearance. Okay. So knowing that, what if the ratio is not 1-to-1? Well, then we have to figure out how are they related. So for example, if I have 2 moles of hydrogen iodide, it yields hydrogen gas and iodine gas, we have to set up this relationship. Our rate of our hydrogen iodide is going to have a negative because it's going to be disappearing, 1 divided by the coefficient. So this coefficient went down here on the bottom. This is equal to the rate of iodine, and here I have 1 as my coefficient, so 1 divided by 1 gives me nothing. It's positive because it's a product and it's forming. So this is our relationship that we are seeing. So here I want to kind of show you how we're going to derive it for how is the rate of ozone disappearing related to the rate in which oxygen appears. So here we have ozone. It's going to be disappearing, so I'm going to put a negative. Remember, it's always 1 over the coefficient, so here my coefficient is going to go on the bottom. And then I'm going to say this is multiplied to the rate of ozone. So remember, rate is the change in your concentration divided by the change in time. This is all going to equal my rate of appearance of oxygen. So appearance, this is going to be a positive value. I have to put 1 divided by my coefficient, which is 3. And this is all multiplied by my rate. So my change in O2 divided by change in time. And so this is how they are related to one another. Okay. So if you get a problem like this, you can actually use that relationship to help you understand how to solve for this. So if we look at this, I'm going to rewrite that relationship down here so we have something to kind of look at. So I'm going to take a minute to write it down to help us with this problem. Okay, so here it's written down. It says part B on this. If the rate of O2 appears and the rate is 6.0 times 10 to the negative fifth molarity per second at a particular instant, what is the rate of O3 disappearing at this same time? So my whole thing that I am trying to solve for is this right here. I'm trying to solve for this value. So this is essentially X, what I put the box around. And I can fill in what I know. I'm still going to have my 1/2, and I'm still going to have my rate. so I don't know this value, that's what I'm trying to find, equals 1/3. And then this right here, I know this rate. It told me it was 6.0 times 10 to the negative fifth. So essentially you can multiply these two and then divide by, and here's the thing. What I see a lot of people happen is they divide by a negative 1/2, but I just want to divide by 1/2. So I want to divide this by 1/2, which gets rid of it on this side. This tells me that negative x, which is okay, the rate of disappearance, that's all that's meaning, is going to be equal to the following. It's going to be equal to, once I solve all that math, 4.0 times 10 to the negative fifth molarity per second. And again, I want this to be positive because rates are always positive. Now, there's another way you can solve this. Because we are working with stoichiometry, we can solve this using stoichiometry as well. You don't have to set it up like we did above. If you use stoichiometry, you can do 6.0 times 10 to the negative fifth molarity per second of, and this is for O2, and you can actually multiply it by your mole ratio. And so here you can put in our equation, if you look back, O2 was 3 moles. So you can put 3 moles of O2 on the bottom. And if you look back at the equation, I had 2 moles of O3. So here I have 2 moles of O3. You can actually solve this out. And what happens is moles end up canceling, and you're still left with this molarity per second, which is the unit you want. And this still gets you the same answer of 4.0 times 10 to the negative fifth molarity per second. And this is just molarity per second of your O3 appearing. So you can solve it either way. Most people like the bottom. That's the way, the shortcut that I found in college. And so if it works for you, go ahead and use it. Here, I'm going to have 2 more practice problems. If you like doing it whichever way, you guys can choose that way. If you want to pause the video and then work it out, see if you get the right answer. Hopefully you paused it and worked it out. I'm going to solve it the stoichiometry way because I think it's easier for a lot of people. So here it says I have 4.2 times 10 to the negative 7th molarity per second. And this is for the rate of decomposition of N2O5. So N2O5. What I'm going to do is I'm going to set this up. So here I have 2 moles of N2O5, and I want to try to find the rate of appearance of NO2. So here I have 4 moles of NO2, and then you can solve this out. Remember, my moles and moles cancel, and so hopefully for this one, you get 8.4 times 10 to the negative 7th molarity per second, and again, this is for NO2 appearing. And here's the last one. If you want to try to pause this one, go ahead and do so, and let's see if we get the right answer. Here, this one is just like the last one. You're going to start out with your 4.2 times 10 to the negative 7th molarity per second of your N2O5, because that's what I'm working with. And we're going to set up my coefficients. I'm going to still have 2 moles of N2O5. And here, I'm trying to find the appearance of O2. So I'm going to have 1 mole, because that's what's in front of it in the equation, of O2. And then you guys can go ahead and solve this. 2.1 times 10 to the negative 7th molarity per second. And this, again, is my rate of my O2 appearing. Before you go, I just kind of want to point this out. One way to check yourself on these problems is oftentimes your coefficient is going to tell you if you appear or disappear faster than another product. So if I look at this reaction, the one with the biggest coefficient is NO2. So you should calculate NO2's number being bigger than any of the others. And we're going to see 8.4 is still bigger than 4.2, and it's still bigger than 2.1. So that makes sense. The one that's going to disappear the slowest is going to be the one with the lowest number. So here my O2 is lowest. Notice that it's going to be the lowest number here. So it is, again, the lowest number. That is the end of today's lesson. If you have any questions, please make sure you ask. And otherwise I hope you guys have a tremendous and a great day.